Welcome. Let your shoulders drop and let your eyes rest half closed if they wish. There is nowhere to be tonight, nothing waiting for you but this old story. We are going to walk backward through time, toward the ocean, toward the dark, toward the small fires sailors once lit against a sky that told them where they were. Just listen, and let the hours loosen around you. Long before ships or maps, early humans lay on open ground and noticed the stars kept their places. Night after night, the same bright points returned in the same patterns overhead. A hunter watching the sky from a hillside could see that while the moon changed shape and wandered, the stars themselves did not rearrange. This steadiness, noticed by firelight thousands of years ago, became the first quiet foundation of all navigation to come. Certain stars, ancient peoples noticed, never dipped below the horizon at all. These were the circumpolar stars, turning in slow circles around a fixed point in the northern sky. Herders in Mesopotamia and farmers along quiet river valleys watched them wheel through the seasons without ever setting. A star that never left the sky became, without anyone naming it so, the sky's own steady anchor. In the river cities of Babylon, astronomers began writing down what they saw. Clay tablets, pressed with careful wedge-shaped marks, recorded groups of stars and gave them shapes and names. These were among the very first constellations ever catalogued, sorted patiently by scribes who watched the same sky for generations. Their tablets, baked hard by the sun, still exist today in museum drawers, quietly outlasting the empire that made them. Along the Nile, Egyptian sailors watched for a single bright star before they set out. Sirius, rising just before dawn after months of invisibility, told them the river's flood season was near. Boatmen timing their voyages by this star could plan departures with a confidence the calendar alone could not give them. The river, the star, and the harvest were bound together in a rhythm sailors trusted without needing to understand why. The builders of the pyramids also watched the northern sky and used it with great care. Alignments in several pyramids point toward circumpolar stars, including one called Alnitak, part of the constellation we now know as Orion's Belt. Workers hauling stone by torchlight likely never saw the finished result themselves, yet the alignment endures, a quiet conversation between stone and sky that has lasted over 4,000 years. The star Egyptians once relied on as their fixed northern point was not the pole star we know today. It was Thuban, a dim star in the constellation Draco, sitting closest to true north during the age the pyramids were built. Earth's slow wobble has since shifted that honor elsewhere. Thuban still shines faintly tonight, though it no longer holds the place it once did in the ancient sky. Centuries later, the Greek astronomer Ptolemy compiled a great work called the Almagest. In it, he catalogued 48 constellations, drawing together centuries of older observations from Babylon and Egypt. Sailors and scholars long after his lifetime would still consult his careful lists. Ptolemy worked in the lamplit halls of Alexandria, copying star positions by hand onto scrolls that would outlive the library itself. The Greek poet Aratus once wrote a long poem called Phenomena, describing the constellations and their movements across the sky. Sailors of his time were said to memorize verses from it, using the poem almost like a spoken star chart. Lines of poetry, carried in memory rather than written on paper, guided many a small vessel safely home. Words became, for a while, as reliable as instruments. Homer's Odyssey tells of Odysseus steering his raft by watching the stars through the night. He was told to keep the constellation of the Great Bear on his left hand as he sailed. Whether or not the voyage itself ever happened, the method described was real and familiar to every listener of the poem. Long before instruments existed, this simple act of watching one steady star and steering by it was already old knowledge. Let your breathing find its own slow measure now, no need to guide it. Notice the small pause after each exhale. The quiet gap before the next breath begins on its own. Each time you breathe out, let it last a little longer than the one before. There is no place this breath needs to reach. It simply arrives again and again, like waves returning to the same shore. A small cluster of stars near the northern sky once carried the name Ursa Minor, given by Greek sailors who watched it turn slowly through the night. Within it sat a star they trusted above all others for direction. Fishermen and traders alike learned its shape early, tracing it against the dark water from the decks of small wooden boats. The name has outlasted every ship that ever sailed beneath it. 2 stars at the edge of the Big Dipper's bowl point, almost like an arrow, toward a fainter star sitting nearly still in the sky. Sailors learned to trace a line between them, letting the eye travel outward until it reached that steady point of light. This simple trick required no instrument, only patience and a clear night. Generations of navigators passed the method down by watching, never by writing it in any book. The astronomer Al-Sufi, working in the city of Isfahan during the 10th century, revised older Greek star catalogues with careful new observations of his own. He recorded the positions and brightness of stars with unusual precision for his era, noting some barely visible to the eye. Sailors across the Arab world later relied on copies of his work, carried folded in leather satchels aboard trading ships. His descriptions of certain faint stars remain useful to astronomers even now. Spherical trigonometry, a branch of mathematics refined by scholars during the Islamic Golden Age, gave sailors a way to calculate positions using the curved shape of the sky itself. Rather than treating the heavens as flat, these calculations accounted for the true geometry of a sphere. Scholars in Baghdad and Cordoba worked out formulas that let a navigator convert a star's height into a location on the sea. The mathematics, born in quiet libraries, eventually traveled with merchant fleets far from land. Names like Aldebaran and Betelgeuse still appear on modern star charts, carried forward from Arabic astronomy centuries after those charts first circulated among sailors and scholars. Each name once described something about the star itself, its position or its brightness, spoken in a language far older than the instruments used to study it now. Sailors on European ships later adopted these names without always knowing their origin. The words survived long after the empires that first wrote them down. Arab navigators called their whole system of star knowledge Ilm al-Falak, meaning something close to the science of the celestial bodies. It combined observation, mathematics, and memory into a single practical skill passed from captain to apprentice. A young sailor might spend years simply learning to recognize which star rose first each season. This knowledge was rarely written for its own sake. It lived instead in the daily habits of the sea. A finger's width, held up against the night sky at arm's length, gave Arab sailors a rough but reliable measure called an isba. By counting how many finger widths a star sat above the horizon, they could estimate their position on long open crossings. No brass or wood was required, only a steady hand and years of practice. The body itself became an instrument, carried everywhere the sailor went. The kamal, a simple wooden board strung with a knotted cord, was calibrated to specific stars so a captain could return to a known latitude with confidence. A sailor would tie a particular knot for a particular star and a particular port, then keep sailing until the star matched the same height again. When it did, he knew he had reached familiar waters. The device asked for no writing at all, only a length of cord and a memory for knots. By the time of the Han Dynasty, Chinese astronomers had already recorded detailed maps of the circumpolar stars, the ones that never dip below the horizon. These charts, drawn on silk and later on paper, noted how the stars circled a fixed point in the northern sky through the night. Officials in the imperial court kept such records for both ceremony and travel. Sailors along the southern coast later drew on this same careful tradition of watching the turning sky. A flat wooden board called the Kangsing Ban let Chinese navigators measure how high a star sat above the horizon. The sailor held it at arm's length, sighting along its edge until the star touched the top, then read the marked notches for its height. Different boards served different latitudes, each one a small ladder of measurements. Fleets sailing from southern ports carried sets of these boards, one for nearly every star worth watching. Feel the weight settle into the mattress now, starting at the feet. Let that heaviness spread upward through the ankles, the knees, sinking a little deeper with every breath out. The shoulders lower next, releasing whatever they were holding since morning. Even the jaw grows heavy, the eyelids too heavy to lift. Let the whole body rest like something laid down at the end of a long journey, safe, unmoving, held by the bed beneath it. Jing, his great treasure fleet, sailing in the early 1400s, carried star charts known as star position diagrams. These drawings marked the height of guide stars along known sea roads, stretching from China to the coasts of Africa. Pilots aboard the flagship checked these diagrams nightly, matching remembered star heights to the diagram's careful notes. The charts survive today only in fragments, copied and recopied by later hands. Merchants crossing the Indian Ocean learned to time their voyages by the rhythm of the monsoon winds and by the stars that rose alongside those winds each season. A certain star climbing the eastern sky told a trader the season for sailing west had arrived. Another star's appearance warned that the winds would soon reverse. Ports from the coast of Arabia to the shores of India kept this seasonal star reckoning as carefully as any calendar. A flat sunboard, carved with a small notch and a floating pin, helped Viking sailors judge their course across open water. By day it tracked the sun's shadow. By night, sailors read star bearings instead, holding remembered angles between certain stars and the ship's bow. Crossings to Iceland, Greenland, and beyond depended on this blend of solar and stellar reckoning. No compass existed yet to steady their hand. Old Norse sagas describe sailors steering by the stars when clouds allowed it, though the surviving texts speak of the practice only in passing. The Vinland sagas mention crews watching the northern sky to hold their heading across unfamiliar water. Details of exact methods were never written down. Sailors simply knew, the way a shepherd knows weather. What survives are brief lines, tucked between stories of feasts and disputes and distant shores. Cloudy skies over the North Atlantic left Viking sailors without stars to read for stretches of days at a time. Some archaeologists and saga scholars have proposed that crews carried translucent crystals, later called sunstones, to locate the sun's position even through overcast weather. Whether such stones truly guided ships remains debated, since no confirmed sunstone has ever been recovered from a wreck. The idea endures mostly through later written accounts and careful guesswork. Polynesian navigators memorized entire sequences of stars rising and setting along the horizon, a system later called the star compass. Each point of this compass carried the name of a star that rose or set there through the year. A young apprentice spent seasons repeating these names aloud, night after night, until the whole sky became a map held only in memory. No chart or instrument was needed once the pattern was learned by heart. Rising and setting points of particular stars along the horizon gave Pacific Islanders fixed bearings, much as marks on a compass rose. A star always rose from roughly the same point night after night through a season, so a canoe steering toward that point held a steady course without any instrument. Navigators learned dozens of these points before ever setting out on open water. The horizon itself became the dial, and the stars its numbers. Across Micronesia, navigators carried a mental star compass built from 32 remembered points, each tied to a star's rising or setting place. This entire system lived only in memory, passed from master to student through years of guided practice at sea. A skilled navigator could name the star bearing toward any island he had ever visited. Nothing was drawn, carved, or written. The compass existed only inside a trained and disciplined mind. Atak gave Micronesian navigators a way to measure a voyage without counting distance at all. A reference island, invisible below the horizon, was imagined sliding backward beneath a chosen star as the canoe moved forward. When that star's rising point matched the imagined position of the island, the crew knew roughly how far they had come. The method turned a voyage into a sequence of remembered star island pairings held entirely in the mind. Zenith stars gave Pacific navigators something rarer than a bearing, a fixed marker of latitude written into the sky itself. Certain stars on certain nights passed directly overhead a particular island and no other. A navigator who knew which star stood at the zenith above his destination could watch the sky above his own canoe and know whether he had drifted north or south of the intended line. No instrument was needed, only years of memorized correspondences between stars and islands. Somewhere beyond the edge of the room, a low hum rises and fades, like wind moving through a space too far away to name. It comes and goes without pattern, the way old houses breathe when the night grows still around them. There is no need to place it, no need to follow it anywhere. Let it arrive, let it pass, and let your body sink a little deeper into the place where it rests. Hundreds of Pacific islands, scattered across an ocean too vast to measure by eye. Each had a star assigned to stand above them at the zenith. A trained navigator carried this entire catalog in memory, island after island, paired with its own particular star. Learning it took years, guided by an older master who tested a student's recall night after night beneath the open sky. Forgetting even one pairing could mean missing a landfall entirely. Hawaiian wayfinding traditions, nearly lost by the middle of the 20th century, were pieced back together through study, memory, and contact with navigators from other Pacific islands who still practice the old methods. Cultural historians and native practitioners worked together to recover star paths, seasonal patterns, and the old vocabulary of the sky. The revival grew slowly, built from fragments of oral tradition and careful cross-reference with related Micronesian and Polynesian systems. What had nearly vanished began, piece by piece, to be spoken aloud again. In 1976, a double-hulled canoe named the Hokulea sailed from Hawaii to Tahiti, guided only by traditional star navigation, without instruments of any kind. The navigator Mole Pielug, trained in the old Micronesian methods, steered by memorized star paths, ocean swells, and the flight patterns of birds. The voyage proved, to a skeptical wider world, that the ancient systems could still guide a vessel across thousands of open ocean kilometers with accuracy. It became a turning point in the modern revival of Pacific navigation. Celestial navigation and voyaging traditions of the Pacific eventually earned recognition as intangible cultural heritage, honored for preserving a body of knowledge passed down entirely through memory and practice rather than written record. The designation acknowledged star compasses, wave reading, and voyaging chants as living systems still taught and still used. Communities across Hawaii, the wider Polynesian Triangle, and Micronesia continue training new navigators in these methods today. The knowledge, once nearly silenced, now carries formal recognition as part of humanity's shared inheritance. Aboriginal Australian sky traditions, developed across tens of thousands of years, wove particular star groupings into stories used for direction, season, and travel across vast distances of land and coastline. The emu in the sky, formed from dark dust lanes rather than stars themselves, marked seasonal timing for journeys and resource gathering. Certain star clusters guided travelers moving between waterholes across dry inland country. These traditions, carried through song and story, encoded practical knowledge of the land inside the structure of the night sky. The Southern Cross, one of the most recognizable star groupings of the southern sky, appears on both the Australian and New Zealand national flags, a quiet nod to centuries of navigational reliance on that particular pattern of stars. Sailors moving through southern waters had long used its shape to orient themselves when no landmark was visible. Placing it on a national symbol tied a modern nation back to the older habits of sailors who once read direction from exactly those 5 stars. The Southern Cross served, for centuries, as the Southern Hemisphere's rough answer to the North Star, a marker sailors used to find south when no other landmark offered guidance. A line drawn through its longer axis, extended roughly 4.5 times its own length, pointed close to the direction of true south. Sailors from the age of exploration onward learned to trace that imaginary line by eye alone. It became, for ships far from any coast, one of the most trusted patterns in the entire southern sky. That trusted line through the Southern Cross extended toward the horizon, lands close to south, but never quite exactly there. The true celestial pole sits in a faint, star-poor patch of sky, offering no bright marker of its own. Navigators who traced the cross's axis learned to nudge their estimate slightly, correcting for the small gap between the pointer and the pole itself. It was a workable guide, not a perfect one, and sailors treated it that way. Sigma Octantis sits nearest of all visible stars to that empty patch marking the south celestial pole, though it offers little help to the naked eye. Faint and easily lost among its neighbors, it lacks the brightness that made Polaris so useful in the north. Sailors of past centuries rarely relied on it directly, since spotting it required steadier eyes and darker skies than most decks afforded. Modern astronomers still mark it as the closest approximation the southern sky provides. Polaris, by contrast, sits almost directly above the northern pole, a fixed point around which the rest of the northern sky appears to turn. Sailors north of the equator found in it something the southern sky could never quite offer, a single dependable star holding its place through the night. Ships crossing the Atlantic or the North Sea kept it in view for hour after hour, a marker that barely wandered as the hours passed. Its steadiness became, over centuries, almost a promise. Almost. Let the warmth begin low, somewhere near your feet, a faint heaviness settling into the soles and spreading upward through the ankles. Feel it climb through the calves, unhurried, loosening whatever held tension there. It moves into the knees, the thighs, filling the hips with a slow, low blow. Let it rise higher still, through the chest, the shoulders, down each arm to the fingertips, until the whole body carries that same even warmth, heavy and unbothered, ready for rest. A ship's latitude could be read almost directly from the height of Polaris above the horizon, since the star's altitude in the sky roughly matches the observer's distance north of the equator. A navigator standing near the pole itself would see Polaris nearly overhead, while one near the equator would find it low, almost grazing the water. This simple relationship let sailors judge their position north or south without complex instruments, just a careful sighting and a steady hand. Earth's axis wobbles slowly over thousands of years, a motion astronomers call precession, and it drags the pole star's identity along with it. The star that marks true north today will not hold that role forever, and the star that held it long ago was a different one entirely. This wandering is so gradual that no sailor within a single lifetime would notice it, yet across the span of civilizations, the northern sky's guide star has quietly changed hands more than once. Vega, one of the brightest stars visible from northern latitudes, is expected to take on the role of pole star roughly 12,000 years from now, as precession continues its slow circuit. It held that position once before, in the deep past, long before any sailor charted a course by starlight. The cycle will bring it back again, a reminder that even the sky's most reliable landmarks are only borrowed for a while. The Big Dipper, circling steadily around Polaris through the night, could be read almost like the hand of a clock. Its position relative to the pole star shifted in a slow, predictable arc as the hours passed, and sailors familiar with the pattern could judge roughly how much of the night had gone by simply from where the dipper's handle pointed. Farmers and shepherds used the same trick on land, watching the same turning stars from open fields. Enslaved people escaping northward along secret routes sometimes passed along instructions, hidden inside a simple folk song called Follow the Drinking Gourd, its title referring to the shape of the Big Dipper itself. The song's lyrics carried coded guidance, pointing listeners toward the pole star and the direction of freedom without ever naming a route aloud. Sung quietly around fires or fields, it carried practical navigation, disguised as something ordinary enough to escape suspicion. Frederick Douglass, in his own written recollections, described learning fragments of star navigation from sailors he encountered in his youth near the docks of Baltimore. Watching men who worked the water, he absorbed small pieces of their practical knowledge, including how the North Star could mark direction on a clear night. That knowledge, gathered informally along a working waterfront, later became part of the resourcefulness he carried through his own escape northward. Fomalhaut, a bright star low in the autumn sky, gave sailors south of the equator a dependable marker once the summer stars had faded. Arab and European navigators alike called it by names meaning the mouth of the fish, tracing it to the constellation Pisces Austrinus. Its position, well clear of brighter neighbors, made it easy to isolate even for a tired lookout scanning a crowded horizon. Ships bound through southern waters in the cooler months often logged its altitude as a matter of habit. Canopus, the second brightest star in the entire night sky, served sailors navigating below the equator long before instruments could measure its altitude precisely. Ancient Egyptian and later Arab astronomers recorded it under different names, and Polynesian and Arab sailors both used its position to hold a steady heading through open water. Because it never rises for observers far in the north, its very appearance told a navigator something about how far south the ship had traveled. A glimpse of Canopus above the horizon was, for some crews, confirmation enough that they had crossed into unfamiliar latitudes. Vega, blazing overhead through summer nights in northern latitudes, offered a landmark bright enough to spot even through thin haze. Its steady brilliance made it a favorite reference among sailors plotting position far from shore, especially when Polaris sat low or partly obscured. Arab astronomers named it for a swooping eagle, a name that traveled through centuries of star catalogs into modern charts. Officers on watch learned to recognize its blue-white glow instantly, without needing to trace out the rest of its faded constellation. Arcturus, rising with a distinct orange glow each autumn, gave sailors in the northern hemisphere a seasonal marker as reliable as any calendar. Its position along the arc, extending from the Big Dipper's handle, made it simple to locate even for a novice on his first voyage. Fishermen and merchant sailors both watched for its return each year, treating its appearance as a signal that the nights were lengthening. Old star lore across several cultures linked it to herdsmen and watchmen, figures who, like sailors themselves, spent long hours tracking the turning sky. Somewhere below deck, a lantern burns down to its last inch of oil, the flame narrowing until it is little more than a thread of gold against the glass. Watch how the light gathers itself smaller and smaller, unwilling to hurry toward its own end. Your breath can follow that same unhurried shrinking, each exhale a little longer than the last, each inhale asking for nothing more than it needs. The wick glows on, dim and steady, needing no attention at all, content simply to fade. Rigel and Betelgeuse, the two brightest stars marking the shoulders and feet of Orion, gave sailors two fixed points bright enough to use even from a rolling deck. Rigel's cold blue-white light and Betelgeuse's warmer red-orange glow made the pair easy to tell apart at a glance, useful when a quick bearing mattered more than precision. Sailors crossing tropical waters found Orion especially convenient, since the constellation stands almost upright over the equator. A lookout who knew these two stars by color alone could orient a ship within moments of clear sky appearing. Orion's belt, 3 stars set in a near-perfect line, rises almost due east and sets almost due west when viewed from near the equator. Sailors sailing tropical routes learned to trust this simple alignment more than almost any other trick in the sky, since it required no instrument and no calculation. A glance at the belt against the horizon told a helmsman whether the ship still held its intended heading. Arab, Polynesian, and European sailors independently discovered the same shortcut, each within their own tradition of watching the turning night. 57 stars, chosen over generations of maritime practice, were arranged so that navigators anywhere on Earth could always find several of them visible above the horizon in any season. Bright, well-spaced, and easy to distinguish from their neighbors, these stars formed a working toolkit rather than a random sample of the night sky. Some sit near the celestial equator, others further north or south, ensuring coverage from pole to pole. A sailor who mastered this modest list held in effect a portable map of the entire sky. Hydrographic offices in Britain, the United States, and elsewhere agreed, over the course of the 20th century, on this same list of 57 stars for their published navigational tables. Before that agreement, different nations sometimes favored slightly different sets, leading to small inconsistencies between charts printed in different ports. Standardizing the list meant a British-trained officer and an American-trained one could compare notes without confusion, each reading the same star by the same name. The list, printed in almanacs still issued today, remains largely unchanged since it was settled. Magnitude, the ancient scale ranking stars by brightness, told sailors which points of light to expect, and which might vanish first as haze or moonlight crept in. A star of the first magnitude could push through thin cloud that would erase a fainter one entirely, so navigators leaned on the brightest entries whenever conditions turned uncertain. Officers consulted almanac listings, noting each star's magnitude before deciding which to attempt sighting that evening. This small piece of foresight saved many a watch from wasted minutes squinting at an empty patch of sky. Voyages spanning months demanded foresight beyond a single night sky. A captain planning a crossing consulted almanacs to know which stars would climb into view as the ship moved south or north, or as winter gave way to spring. Rising and setting times shift with the seasons, so a star useful in autumn might sit below the horizon by summer. Experienced navigators memorize these seasonal rhythms, the way a farmer learns when frost will come. Thick cloud could swallow a navigator's chosen star without warning. Rather than wait helplessly for a clearing, sailors trained themselves to scan other regions of sky where a second, third, or fourth candidate might still be visible. A watch officer who knew several usable stars in different quadrants rarely lost an entire night's observation to weather. This redundancy, built from long practice, turned an uncertain sky into something workable. Stars sit at distances so vast that a ship's motion across an ocean barely shifts their apparent position. This steadiness made them dependable reference points, unlike wandering lights closer to home. A star observed from a harbor in Lisbon appeared, for practical navigational purposes, in the same place as when seen from a deck off the coast of Brazil. That unchanging quality was the quiet foundation beneath every method sailors built atop it. Planets, though bright and easy to spot, moved against the background stars in ways that complicated calculation. Older navigational tables often left them out entirely, favoring only the true fixed stars whose positions could be trusted year after year. A sailor, mistaking a planet for one of the reliable reference points, risked a small but real error in a latitude reading. Caution, more than ignorance, kept the wandering lights off many working charts. Astronomers found it useful to imagine every star fixed to the inner surface of an immense, invisible sphere surrounding the Earth. This celestial sphere ignored true distance entirely, treating each star as though it hung at the same remove, differing only in direction. The model simplified centuries of calculation, letting navigators plot positions with angles rather than wrestling with the true scale of space. It was a convenient fiction, and a remarkably useful one. Let the muscles around your eyes soften first, the small tension at the corners easing away. Feel your eyelids grow heavier, as though each blink takes a little longer to lift than the last. Let your jaw unclench, your lips part just slightly, the whole lower half of your face settling into stillness. Behind your closed eyes, there is only a slow, dim darkness, warm and undemanding, asking nothing of you but to remain right where you are. Astronomers needed a way to mark exact positions on that imagined sphere, much as mapmakers mark points on Earth. Right ascension measured a star's place running east to west, like a celestial longitude. Declination measured its distance north or south of the equator, mirroring terrestrial latitude. Together, these two coordinates let a navigator locate any star in the sky with the same certainty a mapmaker locates a city on land. A star's hour angle described how far it had traveled westward from the observer's own meridian, that invisible line running from north to south directly overhead. Measuring this angle told a navigator not just where a star sat in the sky, but how much time had passed since it crossed that overhead line. The hour angle connected the turning heavens directly to the ship's own position, tying two vast systems, sky and sea, into one working measurement. When a star crossed the meridian directly overhead of an observer, reaching its highest point in the sky, navigators called this meridian passage. At that exact moment, measuring the star's altitude gave a latitude reading of unusual precision, free from many of the small errors that crept into other calculations. Officers timed their sightings carefully to catch this brief instant, often waiting on deck with instrument raised, watching the star climb toward its peak. Long before longitude could be reliably calculated, sailors relied on a method known as latitude sailing. A captain would sail north or south until reaching the known latitude of his destination, then simply hold that line east or west until land appeared. It was a patient, roundabout way to cross an ocean, trading efficiency for certainty. For centuries, this simple technique carried ships safely to distant coasts long before any clock could measure longitude at sea. A wooden rod with a sliding crosspiece served sailors long before any sextant existed. The cross staff required a navigator to hold one end against his cheekbone, sliding the crosspiece until its edges touched both horizon and star. Reading the angle from marks etched into the wood, he could work out his latitude. It was awkward, forcing the eye to strain at 2 points at once, but for generations it was the only tool available. Sailors needed something lighter and quicker than the astronomer's instrument, crowded with dials and rings. The mariner's astrolabe stripped away most of that complexity, leaving only a heavy brass ring meant to hang steady from a thumb even on a rolling deck. A pivoting arm, called an alidade, swung along a scale marked in degrees. Stripped of ornament, built for salt air rather than a scholar's study, it answered one question only: how high above the horizon did a star stand? Merchants and scholars carried the astrolabe from workshop to workshop long before it ever crossed an ocean deck. Arab navigators in the Indian Ocean and Red Sea used their own refined versions, often smaller and simpler than the astronomers' models kept ashore. European sailors, generations later, adopted the very same principle for Atlantic crossings. The instrument passed between cultures much as knowledge itself often does, reshaped slightly with each hand that held it, yet never losing its original purpose. Arab sailors crossing the Indian Ocean carried a device far simpler than any brass ring. The kamal was little more than a small wooden card threaded through a knotted string, held at arm's length toward a chosen star. Each knot, gripped between the teeth, marked a known altitude corresponding to a familiar port's latitude. A sailor sighting his home star through the card at the correct knot knew he had reached the right line to turn toward land. By the 1700s, instrument makers in London and Paris had solved a problem that had troubled navigators for centuries. The sextant used mirrors to bring the star and horizon into the same field of view at once, ending the old strain of judging two distant points separately. Its arc, precisely divided, allowed readings finer than any wooden staff could offer. Within a few decades, ships from every major seafaring nation carried one below deck in a fitted wooden case. At its heart, the sextant performed one elegant trick with mirrors and glass. A navigator adjusted the instrument until the reflected image of a star appeared to touch the true horizon, seen directly through a small telescope. The angle between them, read from the graduated arc, gave the star's altitude above the sea. From that single number, with a few more steps, a ship's position on the wide ocean could be drawn out on paper. Let the breath slow now, each inhale a little quieter than the one before it. Feel the exhale stretch out, longer than you expect, like a tide easing back from shore. There is no need to hurry it, no need to count it. Just let the next breath arrive on its own, and the one after that, further apart, until the space between them feels wide enough to rest inside. Sailors had a phrase for the moment. They raised their sextant toward the heavens. To shoot a star meant lining up the instrument, waiting for the right second, and capturing that fleeting angle before the ship's roll disturbed the reading. The word carried none of its usual meaning here, only the sense of aiming carefully and catching something quick before it slipped away. Officers wrote the results into their logbooks in that same plain language, star after star, night after night. Neither full daylight nor full darkness suited the navigator's purpose. In daylight, the stars vanished, and in deep night the horizon itself grew impossible to see clearly. Twilight offered both at once. A brief window when the sky still held enough glow to outline the sea's edge, yet had darkened enough for the brighter stars to appear. Officers learned to treat this narrow stretch of time as the workhorse of their trade, gathering as many readings as they could before it passed. Astronomers divided that fleeting window into finer bands, and sailors learned to watch for two of them above all others. Morning nautical twilight arrived before sunrise, when the horizon sharpened while the stars still burned above it. Evening nautical twilight offered the same balance in reverse, after sunset, but before the sky went fully dark. Within these short stretches, often lasting only a matter of minutes, a skilled officer could gather several star sights before the chance slipped away entirely. Fog and haze could swallow the horizon completely, leaving nothing for a sextant to rest against. In such moments, navigators turned to an artificial horizon, a small basin of mercury, or a bubble level fixed to the instrument itself. This substitute mimicked the true line where sky meets sea, giving the observer something steady to measure against. Aviators later relied on the same trick, since clouds hid the horizon far more often above the ocean than below it. Light bends as it passes through the thickening air near the horizon, and that bending misleads the eye. Refraction correction accounted for this, and its value grew largest exactly where stars sat lowest in the sky, close to the sea's edge. A star measured high overhead needed almost no adjustment at all, while one hovering just above the horizon might be displaced by a noticeable margin. Navigators kept printed refraction tables folded into their almanacs, consulting them by lamplight before trusting any low reading. Standing on a tall deck lifted the observer higher above the water than standing on a small boat, and that height changed what the horizon appeared to do. Dip correction adjusted for this difference, since a taller vantage point let the eye see slightly farther, pushing the visible horizon lower than it would appear from sea level. Officers noted their eye height above the waterline before every set of sights. A tall clipper and a low fishing sloop required different corrections for the very same star. Nearby objects like the moon shift position depending on where an observer stands, an effect called parallax. Stars sit so far away that this shift becomes too small to matter, vanishing into rounding error long before it could disturb a navigator's calculation. This simplicity was part of what made stars such trustworthy markers across centuries of seafaring. A sailor could stand at either rail of the ship and see the same star in what was, for all practical purposes, the identical direction. Polaris does not sit precisely at the celestial pole, but circles it at a small distance, tracing a modest loop in the sky each night. Because of this offset, latitude found from Polaris needed a small correction depending on the star's position in its loop at the moment of sighting. Navigators consulted tables that gave this adjustment based on the hour and the season. Without it, a position could drift by a small but meaningful margin, enough to matter after weeks at sea. Christopher Columbus carried a sea astrolabe and a quadrant across the Atlantic, measuring the North Star's height above the horizon to judge how far north or south his ships had traveled. His logbooks, later summarized by the historian Bartolomé de las Casas, describe these readings taken from the rolling deck of the Santa Maria. The technique gave him a rough sense of latitude, though the tools of his era offered little precision. Still, it was one more thread holding his course together across unfamiliar water. Columbus recorded readings that puzzled him, since Polaris seemed to shift position depending on the hour of the night. He noted these irregularities in his log without fully grasping their cause, describing the star as behaving unpredictably. Modern historians recognize this as the natural loop Polaris makes around the true pole, a movement too small for his instruments to resolve properly. His confusion, preserved in his own words, offers a rare glimpse of a navigator wrestling honestly with an imperfect sky. Let the weight of the body settle now, starting wherever it rests heaviest. Feel your shoulders sink a little further into whatever holds them, as though the mattress had grown a fraction softer just to receive you. Let that heaviness travel down through your arms, into your hands, until even your fingers feel too heavy to curl. Let it move into your hips, your knees, your ankles, each part giving its weight over fully, sinking a little deeper than the part before it, until your whole body rests like something set down at the end of a long day. Ships rounding the southern coast of Africa in the 1400s brought back reports of a sky unlike any seen from European harbors. Portuguese sailors described 4 bright stars arranged in a distinct cross shape, visible only after crossing into far southern latitudes. Their written accounts, among the earliest European descriptions of the Southern Cross, treated the constellation as a striking curiosity worth recording in ship's logs. To sailors raised under Polaris, this new marker in an unfamiliar sky must have felt like proof of how far from home they had truly sailed. Prince Henry the Navigator gathered pilots, cartographers, and instrument makers at his court on the southern coast of Portugal, tasking them with solving the problems of unfamiliar seas. Under his patronage, navigators compiled star altitude tables recording how high certain stars stood above the horizon at various latitudes. These tables let sailors compare a fresh reading against known values, estimating their position without needing a fixed pole star overhead. The work, carried out through the middle of the 1400s, laid groundwork that later Portuguese expeditions would depend on for decades. A single manual known as the Regimento do Astrolabio circulated among Portuguese pilots through the 1500s, gathering star tables and instructions into one practical guide. Copies were kept aboard ships bound for India and Brazil, their pages worn soft from handling in salt air. The booklet explained how to measure a star's height, and convert that reading into latitude, turning years of court research into something a working sailor could carry in a coat pocket. It became one of the first standardized handbooks for celestial reckoning at sea. Vasco da Gama's fleet, pushing around the southern tip of Africa toward India in 1497, depended on star sightings to hold a steady course far from any coastline. His pilots took readings of Polaris while it remained visible, then shifted to southern stars once the northern sky dropped away entirely. Portuguese records describe this changeover as a delicate period, when familiar markers vanished and new ones had to be trusted before they were fully understood. The voyage proved that star-based reckoning could carry a fleet across oceans no European had charted before. Maps drawn by Renaissance cartographers often carried more than coastlines and compass roses. Along their borders, mapmakers added small tables listing star altitudes for various latitudes, effectively printing a navigation manual onto the chart itself. A sailor unrolling such a map in a candlelit cabin could check his position against these figures without consulting a separate book. This blending of geography and celestial instruction reflected how deeply star observation had become woven into the ordinary tools of seafaring life. Mediterranean sailors of Marco Polo's era carried portolan charts, detailed coastal maps marked with compass lines radiating from small stars called wind roses. Yet even these charts, prized for their accuracy along known shores, offered little help once a ship lost sight of land. Pilots supplemented the charts with nightly star observations, using familiar constellations to hold a bearing between the marked headlands. The two systems worked together, paper guiding the coastline and sky guiding the open crossing. The magnetic compass, for all its usefulness, never fully replaced the sailor's dependence on the stars. Its needle pointed toward magnetic north, a direction that drifted from true north by varying amounts depending on where a ship sailed. Pilots crossing from European waters into the Atlantic noticed their compass readings shifting in ways that puzzled early navigators before the cause was understood. Only the fixed stars, unaffected by the Earth's shifting magnetism, offered a reliable check against these unexplained errors. Sailors eventually learned to measure the gap between magnetic north and true north by comparing compass headings against star bearings taken on clear nights. This difference, later named magnetic declination, varied from region to region and had to be recorded fresh in each new stretch of ocean. Ships' logs from the age of sail contain long columns of these corrections, built up voyage after voyage. The work was tedious, but it kept compass, guided courses honest against the steadier authority of the sky. Because the North Star sits so close to the Earth's axis of rotation, its position in the sky changes little through the night. Navigators used this steadiness to check whether their compass was reading true or drifting off course. A pilot could take a bearing on Polaris, compare it against the compass heading, and calculate the exact correction needed for that stretch of sea. This simple cross-check, repeated for centuries, quietly kept countless ships from wandering unnoticed off their intended path. Dead reckoning let sailors estimate their position using speed, heading, and elapsed time, but small errors accumulated with every hour at sea. To guard against drift, officers took star sightings each clear night, comparing the calculated position against what the stars indicated. Discrepancies were noted, discussed, and folded into the next day's estimate. This nightly ritual, part arithmetic and part patience, turned rough guesswork into something closer to a dependable record of a ship's true track. Somewhere below deck, a low creak moves through the timbers and fades again. The way old wood answers the sea without meaning to be heard, it comes and goes, unhurried, as if the ship itself were breathing in its sleep. Listen for it without searching, the way you might notice rain long after it started. Let each small sound arrive, settle into the dark around you, and drift away again, taking a little more of your waking mind with it each time. Aboard many sailing ships, the officer on watch kept a night order book, a written record left for whoever stood the next watch through the dark hours. Alongside sailing instructions, it often listed which stars should appear at certain times, so a tired officer could confirm the ship's heading without waking the captain. A quick glance skyward, matched against the expected names written in ink, offered a small private reassurance that all was proceeding as planned. Sailors returning to a familiar harbor often carried more than memory to guide them home. Many kept private notebooks listing the altitude of a chosen star as measured on earlier visits to that same coastline. On a clear night approaching land, a pilot could take a fresh sighting and compare it against those old figures. A close match meant the ship was holding its known approach, a quiet confirmation gathered from the sky rather than any chart. Before dependable clocks could survive a rolling ship, sailors needed another way to fix their longitude at sea. The lunar distance method measured the angle between the moon and a chosen star, then compared that angle against predicted tables to reveal the exact time at a reference meridian. From that time difference, longitude could be calculated with patient arithmetic. The work was slow and demanded a clear sky, but for decades it stood as the most trusted method available. Neville Maskelyne, appointed Astronomer Royal in England, spent years refining the lunar distance method into something ordinary navigators could actually use. He organized the calculations into published tables, sparing sailors the burden of solving complex spherical equations by hand at sea. His work turned an elegant but difficult idea into a practical shipboard routine. For a generation of officers, his name became attached less to the stars themselves than to the tables that made reading them possible. By 1767, a new volume began appearing in ship's chests across the fleets of Europe. The Nautical Almanac gathered lunar distances, star positions, and time predictions into a single annual publication, replacing scattered private notes with one shared reference. Officers no longer needed to calculate everything themselves. Much of the heavy arithmetic had already been done ashore. Copies grew worn and salt-stained within a single voyage, their pages consulted nightly under swinging lamplight. John Harrison's marine chronometer, perfected after decades of careful craftsmanship, eventually offered sailors a different path to longitude altogether. Instead of measuring angles among moon and stars, a navigator simply needed to know the correct time at a home port and compare it to local noon aboard ship. The device kept steady time through storms and temperature swings that had defeated earlier clocks. Where lunar distances demanded patience and skill, the chronometer offered a quieter kind of certainty, ticking on regardless of the weather outside. Even after chronometers became common aboard ship, star sights never disappeared from the nightly routine. A chronometer could drift or fail without warning, and no captain wanted to discover the error only after running aground. Officers kept taking star sightings to verify that the ship's clock still agreed with the sky above it. In this way, the oldest method of navigation remained a quiet safeguard against the newest one, each checking the other through every voyage. Sight reduction tables took the raw angle of a star sighting and turned it into something a tired officer could use without slow trigonometry. Rather than solving spherical equations by hand each night, a navigator could look up pre-computed values matched to an assumed latitude, longitude, and the star in question. The tables condensed years of mathematical labor into a few columns of printed numbers. What once required a trained astronomer's patience could now be managed at a small desk by lamplight in under an hour. Navigators working with sight reduction tables began each calculation from a starting guess called the assumed position, a rough estimate of where the ship believed itself to be. From that assumed point, tables predicted what a given star's altitude and bearing should look like. The actual sighting was then compared against that prediction, and the difference revealed how far the assumed position had drifted from reality. It was less a direct answer than a careful correction, built one measured star at a time. One star sight, carefully measured and corrected, does not give a fixed point on the chart but a line. Every location along that line would produce the same observed altitude for that particular star at that particular moment. The navigator drew this line across the chart, knowing the ship stood somewhere upon it, though not yet exactly where. A single line offered only part of the answer, waiting for another star to complete the picture. Let the warmth begin low, somewhere near your feet, a mild heaviness settling into them like sun-warmed sand. Let it rise slowly into your ankles, then your calves, spreading the way heat moves through a stone left resting in the afternoon light. Feel it climb into your knees, your thighs, unhurried, in no rush to reach anywhere at all. Let it pool in your chest for a moment, steady and even, before easing into your shoulders, down your arms, into your fingers, until warmth has quietly claimed the whole of you. 3 star sights, taken in careful sequence, could pin a ship to a single point on the chart rather than a mere line. A navigator chose stars spread across the sky, one to the north, one to the east, one to the west, so their lines of position would cross at sharply different angles. Where those 3 lines met, or nearly met, marked the vessel's true location. It was patient work, 3 separate aimings at the dark, each one narrowing the unknown a little further. The cocked hat was the small triangle formed when 3 star lines failed to meet at one exact point, as they almost always did. Named for its resemblance to an old 3-cornered hat, the shape revealed the natural imprecision hidden in every human measurement. Navigators learned to treat the center of that triangle as the most probable position, rather than despair over the mismatch. A small cocked hat meant a confident fix, a wide one meant the night's sightings needed to be taken again. A running fix let a navigator combine sightings taken minutes or hours apart, when only one clear star could be found in the sky at any given moment. The earlier line of position was advanced forward on the chart, adjusted for the distance and course the ship had traveled since. Where that shifted line crossed a fresh sighting, a fix could still be drawn. It was a way of borrowing from the past to complete an answer in the present. Captain James Cook carried both lunar distance tables and a steady practice of star sighting through his voyages across the Pacific, aboard vessels like the Endeavour. His officers measured the angle between the moon and chosen stars, checking their reckoning against printed almanac figures. Cook trained his crew rigorously in these methods, insisting that accuracy mattered as much as courage. His logbooks, still kept in archives today, show pages of careful celestial calculation beside notes on wind and current. Cook's insistence on precise star and lunar observation gave his charts of the Pacific an accuracy earlier explorers had rarely achieved. Coastlines he plotted around New Zealand and eastern Australia matched, in outline, what satellite mapping would later confirm centuries afterward. Positions fixed by star and moon, rather than guesswork, meant future sailors could trust his charts enough to follow them into unfamiliar waters. It was measurement, patiently repeated night after night, that turned exploration into lasting knowledge. Naval officers of the age of sail could not rise in rank without proving themselves capable at the stars. Examination boards tested a candidate's ability to take a sight, correct it, and work the resulting figures into a usable position. A young lieutenant might spend years practicing on deck before an examiner judged him ready. Skill with a sextant and a set of tables was, for centuries, inseparable from the idea of being trusted to command a ship. The clipper ships of the middle 1800s raced across oceans on schedules that left little room for uncertain positioning. Vessels like the Cutty Sark, carrying tea from China or wool from Australia, depended on their officers taking sights every clear night to hold the fastest possible course. A wrong turn or a missed current could cost days on a voyage where speed itself was the cargo's value. Celestial navigation in that era was as much a matter of profit as of safety. The tool known as the 2102D Star Finder gave sailors a quick way to identify which stars would be visible from their position on a given night. Made of thin, layered plastic or card discs, it could be rotated to match latitude and time, revealing the names and positions of stars above the horizon. What once required memorized star charts and careful calculation could now be checked in moments with a simple turn of the wrist. Even so, it demanded a working knowledge of the sky to use well. Star charts prepared for navigation were divided into bands of declination, grouping stars by how far north or south of the celestial equator they lay. A sailor searching for a usable star could scan the band matching the ship's rough latitude, narrowing the search before ever lifting a sextant. This banding turned an overwhelming sky into a set of manageable sections, each holding only the stars relevant to a particular stretch of ocean. Order, applied to the stars, made the search for one useful light far shorter. Radio navigation, arriving in the early decades of the 20th century, offered sailors a new voice to listen for instead of a new light to watch. Shore stations began broadcasting signals a ship could use to estimate its position day or night, regardless of cloud or fog. For the first time in the long history of sea travel, a clear sky was no longer the only path to knowing where a vessel stood. Star sights remained aboard, but their place at the center of navigation had begun, quietly, to shift. Picture a candle on a windowsill, its flame narrowing hour by hour into a single thread of smoke. The wax has pooled and hardened in ridges down the holder, each ring marking a portion of the night already spent. No one tends it now. It simply burns itself down at its own unhurried pace. Let your breathing find that same slow narrowing, thinning toward stillness, needing nothing more from you than to keep on, faint and steady, until it settles into rest. Radial beacons and the system called LORAN spread across coastlines through the middle of the 20th century, giving ships another way to fix their position. Signals crossing from paired stations let a navigator plot a location without ever glancing skyward. Yet officers kept taking star sights on clear nights regardless, treating the radial fix as a companion rather than a replacement. Equipment failed, signals faded with distance, and the stars, unlike any station ashore, never once went off the air. Aviators flying at altitude faced a problem sailors never had, a moving deck of air with no horizon to steady a sextant. Engineers answered with the bubble sextant, an instrument holding a small artificial horizon inside a glass bubble, leveled by the pull of gravity rather than the line of the sea. A navigator could brace it against a shoulder or a bracket in the cabin and still take a workable star sight thousands of feet above the clouds. The old craft simply adapted itself to a new kind of vessel. Before radio beacons stretched reliably across oceans, long-haul flights depended on a navigator seated apart from the pilots, working stars through a small overhead hatch. Early transoceanic aircraft carried a dedicated crew member for exactly this task, plotting lines of position much as a ship's officer would, only faster and with the added burden of a craft in constant motion. The methods were borrowed almost whole from the sea, adjusted only for wind drift and the thinness of high air. Charles Lindbergh, crossing the Atlantic alone in 1927, carried tools for dead reckoning and kept a wary eye on the stars when the weather allowed it. His single-engine aircraft held no radio navigation aid worth trusting over open water, so a scrap of celestial checking and careful compass work carried much of the burden. Fog and cloud often denied him a clean sight, leaving long stretches where instinct and arithmetic mattered more than any glimpse of the sky above the wings. Pan American's clipper flying boats, crossing the Pacific and the Atlantic through the 1930s, carried trained celestial navigators as standard crew, working from a small compartment behind the cockpit. These aircraft, heavy and slow by later standards, spent many hours over water, with no landmark and often no reliable radio signal from the nearest shore. A navigator's nightly sequence of star sights, logged and corrected by hand, was often the only thing confirming that the great machine was still on its intended path. Global Positioning System satellites began reaching orbit in the 1970s, with the full constellation completed by the 1990s, and the change they brought arrived faster than any before it. A receiver small enough to hold in one hand could now report a position accurate to a few meters, in any weather, at any hour. Celestial navigation did not vanish, but for routine voyages it slipped from daily necessity into something closer to a held-in-reserve skill, practiced more from care than from need. Submarine crews, once their vessels broke the surface, sent an officer topside with a sextant much like any surface ship's navigator. Beneath the waves, a submarine's instruments could drift from true position over hours of running submerged, accumulating small errors no onboard gauge could fully correct. Surfacing at dusk or before dawn offered a chance to catch stars, confirm the vessel's place on the chart, and submerge again with confidence restored. The stars asked nothing of the sea state or the hull below them. The United States Naval Academy has kept celestial navigation in its curriculum long after satellites made it unnecessary for daily use, teaching midshipmen to shoot stars with a sextant much as officers did a century before. The reasoning offered is simple. Satellite signals can fail, be jammed, or be spoofed, and a navigator who has never practiced the older method has no way to check a sudden loss of guidance. When classrooms hold both a modern receiver and a sextant on the same shelf, one behind the other in trust. Officers seeking certification to command cargo vessels still sit examinations in celestial navigation, working through sight reduction by hand, even aboard ships equipped with satellite positioning throughout. Maritime training programs treat the skill as a form of insurance, a backup method that costs little to maintain and could, on the rare occasion of a system failure far from land, matter a great deal. The pencil, the almanac, and the sextant remain part of an officer's required kit, tucked beside instruments far newer and far more often used. A body of maritime law, adopted by nations that rely on the sea for trade, still requires certain vessels to carry the means for celestial navigation. The regulation does not name the sextant outright, but training standards written under it assume one exists somewhere aboard, wrapped and ready. Inspectors checking a ship's certification may ask to see it produced from its case. Paper endures where signals sometimes cannot, and the law was written with that plain fact in mind. Let the jaw loosen now, the way a hand opens when it finally sets something down. The muscles around the eyes have been holding a shape all day, and there is room to let that shape dissolve. Behind closed lids, the dark is soft and shifting. No need to watch it, no need to name what drifts there. Let the face grow heavy, the way old wax settles under its own warmth, and rest inside that stillness a while longer. In 2016, the United States Naval Academy announced it was bringing celestial navigation back into its required course of study, a decision reported by newspapers well beyond the halls of Annapolis. The subject had been dropped years earlier, as satellite systems seemed to make it unnecessary. Officials cited the risk of jamming and cyber interference as reason enough to revive it. The story traveled far, in part because it seemed to run backward against the current of progress. Aboard modern cargo ships and naval vessels, a marine sextant still sits stowed in its fitted case, brass and glass unchanged in principle from instruments a century old. It serves now as a backup, called upon only if satellite positioning fails or drifts unnoticed. Officers are required to know its use even if months pass between practice sightings. The instrument asks for nothing electronic, no signal from orbit, only a clear horizon and a star willing to be found. Reports of satellite signals being deliberately jammed or spoofed in contested waters have unsettled navigators who had grown comfortable trusting a screen. Ships have logged sudden position errors, some large enough to place a vessel miles from where instruments claimed it stood. Maritime academies and shipping companies have responded by renewing emphasis on the older skill, reasoning that a method reading directly from starlight cannot be tricked by a false signal sent from the ground. Certain offshore sailing races, drawn up by organizers wary of total dependence on electronics, still require entrants to demonstrate celestial navigation before they are allowed to start. Competitors must show they can find their position using a sextant and almanac, regardless of whether they ever touch one during the race itself. The rule exists as a quiet insistence that the old skill not be allowed to disappear entirely from those who claim to master the sea. Survival courses built around the possibility of total electronic failure still teach star navigation as a final layer of preparedness. Instructors walk students through finding north by Polaris, estimating latitude from a star's height, and reading a rough course from familiar constellations. The lessons are framed not as history, but as contingency. Useful the day every other instrument aboard has gone dark and silent, and the sky remains the only chart still working. Maritime training organizations around the world continue to offer formal certification in astronavigation, complete with written examinations and supervised sextant sightings taken from a ship's deck. The certificate carries weight in licensing for officers on certain classes of vessel, proof that the skill has been tested and not merely claimed. Training centers keep worn brass sextants on hand for students who have never held one, passed from cohort to cohort across the years. Cruising sailors setting out across open ocean today often take up star navigation not as a requirement but as a private safeguard, something learned in evenings before a long passage. Books and small courses teach the basics well enough for an amateur to find a rough position using a plastic sextant and a paperback almanac. For many, the appeal lies less in necessity than in the pleasure of trusting the sky again, the way sailors once had no choice but to do. Phone applications now let a sailor point a camera at the night sky and receive an identified star field overlaid with a calculated position, blending satellite data with old star charts in a single glowing screen. Training programs use these tools to teach beginners the shapes of constellations before handing them a sextant at all. The app cannot replace the instrument in a true failure, but it has become the doorway through which many now first meet the stars their ancestors sailed by. A photograph taken straight up from a ship's deck can now be enough to fix a position at sea. Celestial navigation applications process the image, match the pinpricks of light against a stored catalog, and calculate a location within moments. What once took a careful hand with a sextant, a stopwatch, and a page of tables now happens inside a pocket-sized screen. The stars themselves have not changed, only the instrument reading them has grown smaller and faster. Night vision devices, first built for military use, have found a second purpose, helping sailors pick out faint stars against a washed-out horizon. Amplified starlight through a small eyepiece reveals dimmer points that the naked eye would miss on a hazy or moonless night. Some training vessels now carry these devices alongside traditional sextants, a modern lens layered over an old practice. The sky offers the same stars it always has. The difference lies in how clearly a tired eye can find them. Let the breath slow now, each inhale a little shorter than the exhale that follows it. Feel the air enter without effort, then leave the body in a long, unhurried release, like a tide easing back from shore. There is no need to count or measure it, only to notice how each breath grows longer on its way out, carrying a little more weight from the shoulders each time. Let this rhythm carry you further from the waking hours, breath by breath, toward rest. Modern navigation software has taken over the arithmetic that once filled pages of a navigator's workbook by hand. A few keystrokes now perform in seconds what used to take a trained officer 20 minutes of careful subtraction and table checking under a swinging lamp. The underlying method has not changed since the days of sight reduction tables, only the pencil has been replaced by a processor. Officers still take the sextant sighting themselves. The machine simply finishes the sum. A European satellite named Hipparcos spent the early 1990s measuring the positions of more than 100,000 stars with extraordinary precision. Its readings became the backbone of star catalogs still used by navigators, astronomers, and spacecraft engineers today. The satellite itself has long since gone silent, drifting in its own orbit, but the numbers it gathered continue to guide instruments that never knew its name. A small machine, briefly aloft, left behind a map that outlived its own working life. Spacecraft rely on devices called star trackers, small cameras that recognize patterns of stars the way an old navigator once recognized the shape of Orion or the Southern Cross. By comparing what the camera sees against an onboard catalog, the spacecraft calculates its own orientation in space, called its attitude. There is no horizon up there, no swell to steady a hand, only the stars themselves, unmoving and dependable, exactly as they were for sailors who trusted them centuries earlier. Astronauts aboard the Space Shuttle use star trackers built into the spacecraft to check their orientation whenever they needed a fixed reference beyond Earth's curve. Before computers took over entirely, crew members sometimes cross-checked instrument readings against the stars visible through the shuttle's small windows. It was, in its own way, a distant echo of a sailor squinting at Polaris from a rolling deck, a search for orientation in a place with no ground beneath it at all. The International Space Station keeps its solar panels and antennas correctly angled with the help of star trackers built into its structure. These instruments constantly compare the surrounding star field against a stored map, feeding the station's computers a steady stream of orientation data. Circling the Earth roughly every 90 minutes, the station passes through 16 sunrises and sunsets each day, and through it all, the stars beyond its hull remain the one unmoving reference it can always trust. Deep space probes headed toward other planets carry catalogs of star positions stored in their own memory, allowing them to determine their orientation without any signal from Earth at all. Far beyond the reach of easy radio contact, a spacecraft can look outward at familiar star patterns and calculate exactly which way it is facing. The method traces a quiet lineage back to sailors reading Polaris from a wooden deck, only now the deck is a metal hull crossing empty space. Rovers exploring the surface of Mars use star tracker technology directly descended from instruments once built for ships at sea. At night, when dust storms settle and the thin Martian atmosphere clears, a rover's onboard camera can locate familiar stars overhead and use them to confirm its precise orientation on the ground. A method born from sailors squinting at constellations above the ocean now helps a small machine find its bearings on a rust-colored plain millions of kilometers from any shore. The two Voyager probes, launched in the late 1970s, carried star sensors called star trackers locked onto the bright star Canopus for reference. As they crossed the outer solar system, these sensors kept their cameras and antennas correctly pointed across billions of kilometers, with no deck, no horizon, no human eye involved. Engineers on the ground still spoke of the spacecraft finding its bearings, a phrase sailors once used long before either probe existed. Missions bound for the outer planets and beyond may one day navigate entirely by starlight without waiting on distant signals from Earth. A spacecraft crossing years of empty dark cannot always rely on radio commands arriving in time to matter. Star patterns, unmoving across such distances, offer a kind of certainty that no transmission ever could, the same certainty a sailor once found in Polaris above a rolling sea. Engineers already imagine star trackers refined enough to recognize their own bearings without any human hand guiding the calculation, autonomous systems reading the sky and deciding their course alone. Such a probe, sent toward the stars beyond our sun, would carry no captain, no chart room, no lamplight, only silent instruments watching an unchanging sky. It is a strange, quiet inheritance, the oldest human habit, reading the stars, entrusted at last to machines crossing distances no sailor ever dreamed of.